an accepted aerospace standard. Launch vehicles were treated as single-use hardware, meaning every massive component was eventually jettisoned and destroyed. On a standard rocket, the first stage accounts for 60% of the total manufacturing cost. Traditionally, that multi-million-dollar asset was thrown into the ocean after only 3 minutes of flight. Lowering the barrier to space required abandoning this disposable model entirely. Orbital rockets had to be treated like commercial airplanes, built to fly, land, inspect, and fly again. When the Falcon 9 made its inaugural flight in 2010, it operated on this legacy baseline. Version 1.0 launched with 9 Merlin 1C engines and was designed to be entirely expendable. This graph tracks the vehicle's velocity and altitude. At main engine cutoff, the first stage detaches at the edge of the atmosphere, traveling at hypersonic speeds. The kinetic energy present at this moment is immense. Slamming backward into a thickening atmosphere creates extreme aerodynamic friction. The returning hardware is subjected to intense thermal stress and pressure that would typically tear a metal cylinder apart. Assuming the booster survives the heat, it still has to guide a multi-ton, nearly empty cylinder to a pinpoint location and reach exactly zero velocity the moment it touches the surface. Recovering an orbital booster is not solved by simply adding parachutes. It is a sequential physics problem requiring a radical, iterative hardware redesign. The recovery sequence begins immediately at stage separation. While the second stage ignites to carry the payload into orbit, the first stage must aggressively arrest its own forward momentum. Before slowing down, the booster physically flips 180 degrees in the vacuum of space, pointing its engines into its path of travel. To execute this rotation without atmospheric drag to push against, engineers integrated cold gas nitrogen thrusters near the top of the booster, firing small, calculated bursts to pitch the vehicle backward. To counteract hypersonic momentum, the Falcon 9 transitioned to upgraded Merlin 1D engines during the V1.1 and full-thrust iterations. These engines introduced a critical operational capability, the ability to reliably restart in the vacuum of space. By reigniting a subset of these engines, the vehicle executes a boostback burn. This firing physically reverses the rocket's trajectory, canceling its downrange velocity and pushing it back toward the launch site. The combination of directional thrusters and restartable propulsion transformed the first stage from a passive falling object into a highly maneuverable spacecraft. As the booster drops closer to Earth, it initiates an entry burn. Igniting the engines a second time acts as a massive aerodynamic brake, shedding velocity before the vehicle hits the dense wall of the lower atmosphere. This illustration maps the deployment of hypersonic titanium grid fins. As air thickens, these control surfaces open from the fuselage. They capture oncoming airflow, translating passive drag into active control, acting as rudders to steer the tail-first cylinder with extreme precision. To survive the blistering heat of re-entry, specialized thermal protection coatings were applied to the vehicle's raceways, landing legs, and interstage, shielding vulnerable systems from structural failure. These targeted aerodynamic and thermal upgrades allowed the booster to safely ride the atmospheric friction down to the surface, rather than incinerating on the way down. The final challenge is the landing burn. A single center engine ignites, rapidly throttling its press to balance the remaining weight of the vehicle and slow it to exactly zero velocity at the moment of contact. At the last second, 4 retractable landing legs deploy outward. They lock into place to widen the vehicle's base and absorb the kinetic impact. Not all missions have the fuel margins to return to the launch pad. High-energy orbital deliveries leave the booster too depleted to make the trip back, requiring the deployment of autonomous drone ships pre-positioned hundreds of miles downrange. Perfecting these remote oceanic landings proved that even the most fuel-constrained, high-velocity missions could end with successful hardware recovery. Sticking the landing was the calculated mechanical result of methodically conquering the physics of speed, heat, and precision control. The Falcon 9 Block 5 represents the culmination of this iterative engineering program. It is hardware designed specifically for rapid, high-frequency reusability. Engineers targeted a highly ambitious operational lifespan, flying 10 times with only minor maintenance between launches and up to 100 times with periodic refurbishment. This chart illustrates the exponential growth in booster reflights. Booster 1067 has completed 36 orbital missions. The recovery program has expanded beyond the first stage. Payload fairings are now routinely scooped from the water and reflown, saving millions. These milestones confirm that the aerospace industry's operating model has permanently transitioned. Disposable rockets have been replaced by a sustainable fleet. Systematic reusability directly addressed the initial economic barrier of spaceflight. The cost of placing a kilogram of payload into low Earth orbit has dropped from tens of thousands of dollars to below $2,000. That sudden collapse in price restructured space infrastructure, enabling massive new satellite constellations and opening orbit to new commercial players.